if 8 grams of A is allowed to decompose for 34 minutes, the mass of A undecomposed is found to be 0.70. Remember, we're dealing with strictly first order right now. That's where we are in the PowerPoint. So these are all first order reactions. So the first thing we need to do, which I know you don't have this problem per se, but you should be able to follow along and write it down and do it, all right? Because I added problems so you can be successful, all right? So the first thing we need to do is we know it's first order. I need to know, everybody says, well, half-life of first order equals, 0.693 over K, all right, for a half-life.
How do we know this is first order? We just know this.
As I just said, we're in that part of the PowerPoint packet, first order.
Oh, sorry.
And I wrote it.
Wow.
Okay.
All right, sorry guys.
All right, so for this one, we know it's that, but I don't have a K value. So what am I going to have to do? In order to solve for K, what am I going to have to do? I need to get a K. What do? It's first order. I have amounts. I have an initial amount. I have a time. And I have a final amount. What's that? All right, natural log. So what would I do? ln of A negative KT plus ln of the initial. All right, good. So now, if I pull out ln of A, what is my A? What do I have for this number? You can write down too, Stephen. 0.7. All right, 70. All right. What is my negative K? We don't know what that is. Times time. What's the time? 34 minutes. Everybody ask me, if you got to convert it to seconds, does anything here imply that we need to convert it into seconds? No, it doesn't matter. All right. Plus ln of the initial amount. Is that an 8?
Yeah.
8.00. All right, so the first thing that I would do is get this side kind of tidied up here. Does anybody have what ln of 0.7 equals?
Negative 0.3567.
Like that? You're good? All right. Now I have negative K times 34 plus what? 2.079? All right, what do I need to do now? I'm going to subtract. I'm just going through all the math for some of us. All right, so I'm going to subtract negative 2.079, and I get negative 2.44. 2.44. All right, equals negative K times 34. What do I have to do? All right, divide by 34. And what do you get?
Negative 0.0716.
It should be positive, right?
But you didn't miss a negative.
All right, so what is it? 7?
717.
Yeah.
717?
Yes.
Yeah.
7.17?
No. Point. Oh, 717.
There you go. Like that.
Yep.
Yeah.
Minutes. So yeah, it's a pretty quick reaction. So that's our calculation.
I don't like that. That doesn't look right to me. Okay, what do we have to do next?
0.693 divided by
Something about it just
All right, 0.693 divided by 0.0717 equals what? Negative 9? No, not negative.
Okay.
9.6.
Oh, 9.67.
All right, 9.6 minutes or so, something like that. Okay?
Minutes. I said 6. That's not good.
So I take this, which I just solved for K, gonna put it up there because I had negative and negative, make it positive. Put that up to the top, get my 9.6. All right?
9 minutes.
I'm hoping that's it. Hoping on your exam, if you get that this spring, you'll be just fine. I know it'll be on my test. All right. All right. Now, these two problems. Determine the percent H2O2 that decomposes in the time using K equals 6.4 times 10 to the negative fifth. All right, so again, we are strictly dealing with first order right now. That's the part of the notes that we are in. I want to give you a question that you would see on an exam. All right? This is very typical where you may have to solve for the K value, then you're given this. So you'd have to write the rate law. You'd have to, with the correct, and then figure out K with the correct units, and then be given a problem like this. All right? That's kind of what you're accumulating points. All right, the time for the concentration to decompose. What would I do first, folks? Let's talk about percents. All right?
Oh,
100% is always the what?
initial no.
All right, we represent that using, how do we represent it? This is percent, we're going to represent it with 1. So relative, all right, so 1. So if we're going to be calculating that, what equation do you think we're going to be using? Very similar to the one we used. Could use other equations, but do we have any equation for first order that has an E in it? I don't know, maybe, maybe not. Okay.
Start rate law.
All right, you're not good with that. So the time for the concentration after the reaction begins. Use the value of K. So again, ln of A equals negative KT plus, right? First order. All right, we are trying to figure out what this is. We're trying to figure out this right here. Don't know what that is. So, negative 6.40 times 10 to the negative fifth, second to the minus 1, times time, 600 seconds, plus ln. All right, Stephen, what do I do next?
You would solve for the interval.
Come on, you're that close to an A. Have some enthusiasm. Well, what's the answer? What do you have on the right? What's this? What's that equal? Oh, maybe you use your calculator now. Oh, crazy. Where's your calculator, Teresa? Good. Yeah, what's the whole right side equal? What?
Negative 0.0384.
Negative 0.0.
38.
Everybody get that?
See.
All right, now I have ln of A. What do I need to do in order to figure out what the concentration of A is? Yes?
E to that.
So I'm going to E each side. So I'm going to E this. Okay, well that makes that go. And I'm going to E this. All right, so the concentration of A, well, we're almost there, but not exactly. What do you get?
196.
What do you get? 0.962. Are we done yet?
Units.
Aha! So at this point, remember, this thing has gone for a while, right? 600 seconds. This amount that we have is now gone.
Consumed.
So it's asking how much for the time of reaction. What am I doing? Determine the percent that decomposes at that time. So 1 minus 0.962, and then I'm going to take that number and do what? Times 100. What do you get? 3.7? All right, there you go. 3.77%. Okay, because 0.692, 96% is what you still have remaining. You have used 3.77% has been used. So this half-life, let's calculate the half-life while we're at it. What's the half-life of this? Oh. How would we do that?
0.693 over
All right, so if you had this question and it said, what's the half-life? It's first order over K, which is going to be 6.40 times 10 to the negative 5th seconds to the negative 1. And that gives me what? I don't know about that. 10 seconds?
Wait, no, that's not.
No, it's 10,828 seconds.
That's what I got.
Yeah, no one agreed.
Point
10,828.
Yes.
10,828.
For 180 minutes.
All right?
Or 3 hours. Or 1/8 of a day. Or 156.
All right. So in 600 seconds, let's see if it makes sense. How many half-lives did we go through? How many half-lives occurred in 600 seconds?
That can't be right then.
How many half-lives occurred in 600 seconds? Say it. None. Why?
Because
It takes that many half-lives, that many seconds for one half-life.
Oh.
We only had that many. So that makes sense. Only 3.7%,
Decomposed.
right? Decomposed. What would this number have to be? How long would it take for this number to be 50%?
10,828 seconds.
Are you seeing what I'm saying? All right, try number 5. All right, try number 5. Brought my handy dandy calculator today. I'm feeling pretty empowered. I just want to know who donated this to me, so I would not buy one of these. I'm a TI-83 guy.
TI Inspire.
feeling good? Oh, did I do that wrong?
Oh, no.
Feeling good?
You did it right.
Are you feeling good about that?
Yep.
All right. What am I going to do?
Raise a T. Or raise E. I feel like it would be a good idea to do that, like, making this problem just so that it'll give good sense for how long it should take. You know what I mean? It's like if you look at it and you're just like, holy crap, that flight was 10,000 seconds.
Good.
You could be like, okay, I got 400 seconds.
Everybody feeling good about that? Get it?
You know?
Get it?
Yeah.
Did I do it right?
Yep.
Yay, okay. Did you do it right? All right, let's move on. Second order. All right, those are anything associated with first order. Those would be all the questions that you would see. I'll leave that up for 1 second. Okay, good. All right. Okay, I have 1 half-life. How much is left after you have 1 half-life?
50%.
All right, watch this. Oh, I have 2. If I have 2 half-lives, what's next?
25%.
Based on this information.
4.
4.
Wait, if you.
If I have 3 half-lives, how much? What? 8.
Nailed it.
4.
16.
16. What if I had 5?
13.
What if I had 6?
64.
What if I had 7?
28.
What if I had 8?
256.
What if I had 9? If I have 12? What if I had 10?
1024.
Good job. All right. Do you see what I'm doing? Very
The only reason I know those is from that game 2048.
Yeah.
Oh, I don't even know what that is. The only reason I remember it is because Charlestown Races and Slots, when I graduated college, had blackjack, and you could let it ride up to 1,024. So if you want to let it ride, let it ride. So if you started with 50 cents, 2 quarters, right? You could get 1,024 quarters, which would be how much money?
512. Oh, no.
Not that.
256.
Yeah, a little bit over 256. Yeah, 256. So, so I always did it because I'm a math guy. So I would always do it. I put in $20, 80 quarters, right? I put in the $20, right? And I say play for 2, let it ride, let it ride. Oh, I didn't get it. So then I only lost 50 cents. So I do the next time. I try to get to 124. Inevitably, every time I put my $20 in, I can let it ride all the way up to 1,000. Whatever, 24. All right, just by using it would be 40 tries. And 40 tries, it would let me ride all the way up there. Just they took that game away because I think people figured that out. Okay.
Walking away with like $250.
Yeah, walk out every time, ready to go. All right, second order reactions. So if it's a second order, we're dealing with basically the 1 over the concentration. The rate equals K times the concentration of A squared at any time. And then we have the half-life of 1 over K times the initial concentration for a second order. All right? So these are what we were working on with Noah earlier. So which one of these graphs are we dealing with for second order? This one? This one? All right? So this is always going to be second order. What's this? Just this calculation part. First, this one's going to be 0. So when you do put those numbers in, you get a chart with just concentration and time. You got to figure out which one creates a straight line. And it's really just every time I get a problem, the people that have seen me after school, I literally just take whatever I have and I make new columns. So I kind of know what I'm working with. All right, but most of the time for AP, once in a while I'll get one like that. Okay. Let's try this. All right, given the following information, determine the order of the reaction and the value of K and the reaction constant. Here's my concentration. All right, so this is what I'm talking about. All right, what I would do at this point is do ln of A and then I do 1 over A. In this case, it's going to be this. So let's see, I think I can do ln of 1. I think that's 0. Anybody have ln of 0.5 for me? I just like it when people are with me. And then ln of 0.33.
If you look at that, the natural log of half is 0.693.
What's that? Negative 1.11.
Isn't that interesting?
All right, what'd you say?
Oh, just that the natural log of half of it is 0.693.
Ah, yes. All right, now, if I do 1 over concentration, 1 divided by 1? 1 divided by 1? 1 divided by 0.5? 1 divided by 0.33?
Yes.
3.03? All right, so what do we have for a winner? Do any of those look linear to you?
Yeah, bro.
Yeah, the time.
All right, so this one then, if this isn't linear, no, this would make this, right? That would do that? All right, what would this do? What would this one do? Down? All right, a little bit less. This one, looking like that. All right, so that means that this is second order. All right, because this is a straight line. Right? I always do that. Whenever I get a problem like this, I always figure out which one it is. All right, now, determine the order of the reaction. We did that. The value of K. How can we figure out the value of K? Plug it in. Oh,
Rate law. Just write a rate law.
what are we going to do?
Rate
Rate equals
K times the concentration of
times the concentration of.
A squared.
Ah.
Second one.
Ah.
I get to see this.
All right, so what would we do now for this? Do we have a rate? Do we have a rate? How do we get a rate? Change in const over change in time. Can we do that?
Yeah.
Somebody give me a number?
Negative 0.05.
We could use our calculators if you needed to. You might not need to, I don't know. What do you want me to put here? Let's just do one together so we all know what we're doing. Change in concentration. What can I put here?
1 minus 0.5.
Over.
10 minus 12.
This is going to be a negative anyways. What'd you get? 0.05. Okay. And what is my unit going to be on that?
Molar per second.
Molar per second. Molar per second. Great. Molar per second. Right? Now can we solve for this?
Yeah.
What do I need to do? What do you want to use? One?
Yeah.
Makes it easy.
0.05. Liters per mole.
What is the answer going to be?
Liters per mole second.
Liters per mole second. Does everybody agree with that?
Second order? Yeah.
Okay. I like it. What else do we have to do? The reaction constant. We did that. The value of K. We got to do a reaction constant. What are we going to have to do?
Oh, I just.
Okay. So
Yes, well,
online you have to do 50 what do we end with? 59 through the next 6 problems. It'll be Arrhenius equation introduction that, I mean, some of you, I expect to see some of you, is basically just simply putting it into your calculator as well. So it should not be a problem.